Thank you very much for your kind introduction. First of all, I'd like to appreciate the Polymer Society of Korea for inviting me such a wonderful meeting. It is a great pleasure for me to have an opportunity of talking about the recent results of our research group. The title of my talk today is the precision synthesis of aggregation behavior of novel silicon Copolymers. The purpose is to develop the new method for precision synthesis of novel silicon containing Amphiphilic Copolymers and study the aggregation behavior in solutions and at air water interface. As you know, the characteristic of the amplifier in water make an aggregation by emulsions of dispersion. And at the interface, the air-water interface make a monolayer or surface modification on the solid surface. Carbo RP-SLAM, just a hybrid polyolefin and polysilicon, and they have high thermal and temperature stability and high flexibility and high hydrophobicity. Recently, we have defined the green polymerization of Shiga cyclobutane, like for example, in the case of the polymerization of 1,1-DFCL Shiga cyclobutane in this experimental condition, we have in the case of the 1,1-dimethyl and the 1,1-DHCl Shiga cyclobutane, here 100 conversion and monomer addition, again increase of the polymer yield. As well, in the case the molecular weight of the polymerization is increased with increase in the yield, and polymer index is almost 1.1. So this is an evidence of the ring polymerization occurs in this system. So using this method, we try to make a new Amphiphilic block copolymer. First, leading polymerization of this cyclobutane, and second step is 1,2 tertiary butyl siloxyl methacrylate. You can see the first block polymers monodisperse. The second block polymers also very beautiful monodisperse polymers. So we can change the ratio of M and N as like that. So we can change the composition of the amplifiers. And after that, we hydrolysis of the protective group of cyclobutane, and you can see here it's very famous polymer to hydroxyethyl methacrylate. Polyhalite is very famous amphiphilic polymer. So this part is hydrophobic part, and this part is hydrophilic part. So we can change the net and N like that. And in this study, we change the substitution of the on the sequence side of one methyl, one SU, and also Lucyl, normal Lucyl. And we mentioned after DFSD block HEMA and DESD, this is SQ HEMA, and also DPSD the HEMA. This normal Lucyl group. And the association in methanol we examined using by small X-ray scattering tracks and also small angle neutron scattering. And behavior on monolayers on water surface, we could try to higher experiment and also X-ray the reflectivity measurements. And this is a summary of our polymerization of 3 polymers. I'd like to say okay. Methyl and the SU and non-methyl. 3 kinds of the polymers also make to mono dispersed polymers. And this is a summary of the results of the polymerization. It changes 3 kinds of the polymers. In the case of the dimethyl, DXU, D-novel-C. This is unit of the M and N. You can see here systematically change the ratio of 3 kinds of polymers, block copolymers. These Amphiphilic polymers make in solution. It depends on the packing parameters. Packing shape is like Mises forms structure as a sphere or rod or disc. And also in the surface is make a monolayer hydrophilic part here, hydrophobic part here. So at first we try to make an examination Mises formation of these polymers. In the case of the examine the shape and the size of the Mises, we can use the small angle X-ray scattering flux measurement. In this case, X-ray here and sample diffraction to theta, and we can have such a profile. This is intensity versus 2 phi here. But in these parts, information we can obtain the information of the size of the Mises. And here is the shape of the information on shape of the Mises. And this part is the surface information of the Mises we obtain. So, typical flux profile of changing the ratio of the amphiphilic part and hydrophilic part and hydrophobic part. You can see clearly change the X-ray profile changes clearly change the direction, as you can see here. This is summary of the results. If we change the we maintain the number of the hydrophilic part is same and change to the hydrophobic part. This is the aggregation number change, decrease in this side. But if we maintain the number of the hydrophobic part and changing the hydrophilic part, the so size of the mice is almost similar. This is the increase of the hydrophobicity, the increase of the aggregation number, and overall size independent of the hydrophilic change there. And this is a total of the summary of the 3 different substituents of silicon atoms. In the case of the methyl, methyl, lighter. In the case of the methyl, the size is the smallest in the 3 hydropaths. So you can see here, it's almost depend on the proportion to the size of the substitution of on the silicon atoms. Also, you can see here the aggregation number increase of the increasing of this ratio. And this is the systematic change of these systems. But in the case of the methyl, curious behavior we observe from the flux profile. Here is a different of the, if we change the temperature in the methyl case, size of the biceps increase with decreasing temperature, but these sizes are differences are clear. So we would like to check the smaller cube part, but it's impossible by using a flux experiment. So we are using neutron, small angle neutron scattering. You can see here Q range is below 0.01. We can clearly check the difference of the temperature 13 degree, 25 degree, 50 degree. So these smaller cube parts completely different here we observe by small angle neutron scattering. So this means this is only the result of the analysis. In the case of the low temperatures, disk-like micelles formed in the systems. And part of the ratio of the disk of 13 degree is 0.75, 25 degrees is 0.10, and 50 degrees is completely sphere-like micelles is formed in geometry substituted polymers, copolymers. the reason why such a behavior occurs in this system, we check the thermal behavior of these copolymers. In the case of the polydimethyl cyclosyrup butan, we eventually at 29 degrees TM 29 degrees here. So even in the copolymers, we have such a melting melting point of the crystalline. So we support from this result. We support in the case of the 13 degree, also 25 degrees, a part of the hydrophobic part is make such a this like a sandwich style this makes foaming at low temperature because they make a crystalline in this part. And this is the first part of my photo, and second part is the shape or behavior on the water surface. Let's say they make a monorail, so they form a monorail. So we check by the X-ray diffusivity measurement. And this is the principle of X-ray diffusivity measurement. The X-ray measurement is the technique to measure the dependence of the diffraction on incident and the diffraction numbers. This X-ray reflects the first layer and penetrates X-ray by standard difference. These two X-rays make a interference to X-ray. So from this period, we can obtain the electron density profile normal to the surface. Also, their thickness, surface and interface roughness and density can be determined this method. And this is consumed of simulation of X-ray diffractivity. If interface, they call the fringe physics fringe, oscillating behavior in X-ray curve. If thickness of the layer, the thickness, the distance of two peaks are smaller than thinner one. And also, if the roughness of the surface is so different, interference between two X-ray is not so clear, so this shape is random like this one. So we can obtain from two distance of 2 peak thickness of the layer, and also the shape of the peak. We can estimate the darkness of some of these rays. So we construct the new reflector like this one. This is the air-water interface X-ray diffractivity. We can change the angles, and on this part is the elevator. So we can measure the changing the surface pressure, and we can as a function of surface pressure, we can obtain the reflectivity change in the system. This is three meters, 4 meters. One very small one is, but very exactly we can measure the X-ray reflectivity. This is the X-ray generator. This is the scintillator sensing part of it. And also, yes, on this part, we equipped the LP trap. So this is a sensor. You can change the surface pressure, and you can measure the X-ray reflectivity change of the X-ray. And this is the sample data of my laboratory. This is a solid PDF film on glass plate prepared by importing. In this case, it's over 30 feet we can observe. In this case, this is a thickness and surface roughness, and also interface roughness of the polymer and glass surface. So this is almost the ideal case of we can obtain over 20 physics film. But in the case of on the water, monolayers of the water, such ideal cases also difficult. But anyway, this is the DSPC or DBPC is a sort of chlorine. If we can change the surface pressure, the hydrophobic parts are just standing out. So only the small part, this difference is the order of the angstrom, but you can clearly observe the shift or the peak. So from shift to peak, we can estimate the change of the hydrophobic part, hydrophilic part. So time is limited. Only the typical results I can show here. In the case of the methyl, the Amphiphilic Copolymers, the part of the tema is the same, and substituent of the silicon part of the methyl, the higher isotope are a little different. But we can, this is a summary of the results. You can see here. In the case of the methyl, this is a thickness of the hydrophobic part and thickness of the hydrophilic part. And this part of the tema part is substantially decreasing of the methyl. And if changing the surface pressure, increasing the surface pressure, the thickness of the hydrophobic part and the hydrophilic part also increasing with increase of the surface pressure. It is very easy to imagine the thickness increasing with the increase of the pressure. So, this is the conclusion of my talk. Amphiphilic cyclobutane having methyl, ethyl, and glycine group on silicon atoms of synthesized. In fact, small angle X-ray scattering measurement suggests that this polymer for core shell micelles in methanol and the size and the aggregation number of the micelles increasing the content of polycyclobutane segment and the size of the substitution of silicon atoms. And these polymers have the melting point in the substituted methyl or methyl. In the case of the methyl, has the melting point at 25 degrees Celsius and shows temperature dependence of the association behavior. Small angle little scattering measurement also is the transformation of the micelle shape from core shell sphere to sandwich disk was lowering the temperature. And phi A and X, our measurements show that this block of polymers forms monolayers of water surface and the thickness of the layers increasing surface pressure. I skipped this temperature dependence, but anyway, this experiment clearly showed the characteristics of this block of polymer. Thank you very much for your attention.